think it's high time we go back to working on the CRT oscilloscope project. The last time we finished off with the power supply mostly built, a cathode ray tube hooked up and producing a spot on the screen. One of the issues that came up was the dot wasn't completely sharp, and I first suggested that it might be due to the focusing voltage being a little too low. It was also suggested to me by someone who has a lot more experience working with all sorts of picture tubes that it might be due to the DC voltages going into the tube being not properly decoupled, basically. So I put decoupling caps on most of the pins on the socket and also on the anode voltage and acceleration grid pins, which should basically stop noise from getting in there. This was successful to some extent. It reduced noise a little bit, but it's still very much noticed. I put a little video clip of that on the screen here. What is interesting about this is that it goes away as soon as you switch off the power supply. So while the capacitors are still charged, the dot becomes very sharp until it disappears because it's run out of power. This leads me to suspect two things. Either it is basically the magnetic field from the transformer interfering with the tube, and I feared that that might be an issue, and that is why most oscilloscopes basically had a piece of metal, a metal magnetic shield over the tube. The other thing could be that the regulated power supply is just oscillating a little bit, and that causing it. But for now, I think I'll just live with that and see how this project turns out. And then once we've got a basic oscilloscope, I'll go back in and see where the noise is coming from and how to get rid of it. But I'll prioritize getting the thing working now first before making sure that it works perfectly. The next thing we need to do is drive the deflection plates in the tube. These are vertical and horizontal, and in this tube the vertical ones are further towards the screen than the horizontal ones. So that means that we need a little more voltage on the vertical plates because they're closer to the screen, so we need to put more force in to get the same deflection angle. How we're going to do this is actually very simple. This is the inputs coming in from the power supply, and we've got the center here, and then we've got, I'll just call this V plus and V minus for now, which is basically the upper and lower bounds of the deflection voltage, while this center is the same as the grid 4 voltage. And we've got our deflection plates here. And what I want to do is take two of those, one vertical, one horizontal, and just connect them via large resistance of, let's say, 10 meg to the center. So this is just discharging that capacitor that is formed by them and basically keeps the beam centered while there is no input signal coming in. So now that we got our beam centered, we need to implement some sort of position control, which we'll do in the following way. We'll just connect a large potentiometer between these two, like this. I'll draw this way around. And then we connect this up to this plate. And this is a 1 meg potentiometer. Ideally, I think the resistance of these and this should be fairly similar, but I don't have a 10 meg potentiometer. I might make these a little smaller in the future, but we'll see how it works out. And then for the horizontal, which needs a little less voltage to get all across the screen, because the plates are further back, we'll do the same thing, but we'll have two resistors here of, let's say, 200k, about 200k, and then we'll connect this to our horizontal. And that's basically the position controls. That is horizontal position and that's vertical position done. So let me just put that on the scope prototype and we'll see how it works. So here's the scope prototype, and if I take out my little pointing stick here, you can see these are the two 10 meg resistors that basically go from the center point up here and connect these wires for the deflection plates to the center. And then you can also see this bunch of wires going off here, which I'm sure will be an excellent antenna for all sorts of noise. And these are the pots for the horizontal and vertical position. And I'll put a little video of them working up here. So this is the horizontal deflection. So you can see, if you can, with the light being that bright, the plates that deflect the electron beam horizontally are here, while the ones that do the vertical deflection are up here. You can actually see that by looking in here, but I can't do that on camera. So this needs a little less voltage. And that's why these resistors are here. And these are just connected together because they need the same supply voltages. And then this goes off to the other pair of wires here. And yeah, as you can see, it works reasonably well. With that out of the way and the positioning working, it is now time to think about how to drive the actual signal we want to have on here. And for that, we'll use two coupling capacitors, two rather ugly coupling capacitors. And I'll only draw it for the vertical, but the circuitry on the horizontal is about the same. What you need is a differential driver, and there's a couple common ways of doing that. We can borrow from the amplifier community here. They need phase inverters all the time, or differential amplifiers, to create push-pull circuits with vacuum tubes. And you could use an AC long-tail pair, for example, but I decided on using a paraphase inverter. This is what this inverter will look like. So we've got basically one simple gain stage, which will serve as an amplifier for the incoming vertical signal. And then we have another gain stage here that basically taps off some of the amplified signal here and amplifies it again, and thereby inverts it. If this is set correctly, we'll basically have a signal of equal magnitude here and here, but with the phases inverted. And that's what paraphase means. It's a parallel stage of inverted phase. So, because we need two triodes it's rather convenient to use something like an ECC 81, which should be a 12AT7, I think. And this is just V1, and this is V2. And that makes it nice and compact. And also, in addition to our inverted signal, we also get a lot of gain from this, which is nice because we probably want some gain for our vertical input anyway. Not so much for the horizontal, which will make ourselves with some sort of oscillator, which will already be relatively high in voltage, but for the vertical input, which the signal we want to measure on the oscilloscope or display on the oscilloscope, it's rather nice to have a little bit of gain. I cobbled together a little prototype circuit, and this is basically all of this down here. So let's hook this up to an oscilloscope and see if it actually works. The values I should probably put down here. All of these are 68 nanofarads. We can make these larger in the actual build version. These are 100K. This is 270K. And this is 2.2K. And as you can see, it doesn't have the bypass capacitor on it. I might do that later. But if I'm satisfied with the performance, I might also not do that. Because without it, you'll get less gain, but it will be a more linear response over the frequency range, I think. Although I'm not all that certain about that. But for now, let's just hook this up to an oscilloscope and see how it works. I know this looks rather gruesome, but the circuit under test is down here in this spool of wire. Then we've got power for the filaments coming in here. We've got two probes going off to the oscilloscope. We also have the signal generator feeding in here, a sine wave, into the input. So now let's switch to the oscilloscope and see what it does. Also, the power is coming directly from the oscilloscope. So here's the output on an oscilloscope. And you'll excuse me using this old analog scope instead of the nice digital one I have. But this feels just much more in tune with the spirit of the project. Also, I have this latent fear of blowing up my nice scope by injecting high voltage into its input. So I'll probably use this old analog scope for the rest of the project, which is a little more robust and also a lot less expensive. As you can see here, the two waveforms are inverted. The same moment this peaks, this is at its lowest point. And yeah, this all looks a little bit distorted, but the input coming into it also looks a little bit distorted, so it's actually working rather well. I think we can accept this as our driver for the deflection plates. What I'll do next is I'll put this design on a circuit board and then etch and populate it, and then we can see if that works just as well as this does. I expect it actually to work a lot better because that other prototype is kind of a mess. You can see I laid out, populated and assembled this circuit board here that has the circuit that we discussed previously. That's shown down here on it. Not only does this look rather nicely, it works fairly well. The next step would be to actually put this in the oscilloscope back here, mount it, hook it up to the oscilloscope, and then see if we can deflect the electron beam like we want to. The next step after that would be to make up a second one of these boards, for the other set of deflection plates. And after that, we basically have deflection done, and we might even be able to already put something on the screen that is sensible. Let's just have a small look at how this is hooked in. As before, the power is coming in directly from the oscilloscope. This is plus 400, this is ground. Then the signal is coming in here. This is filament supply, and this is going to the two vertical deflection plates. So I'll switch the camera over to the screen and we'll see how this works. I've got the camera centered at the screen now, and you can see the power is just coming up. What I'll do now is I'll start up the signal generator and feed a 15 Hz sine wave of about 2 or 3 volts into the input of the amplifier. So I've got the signal generator on now. And there we go. I'll just center this on the screen here. What you can see here is that the beam is deflected up and down, just as it's supposed to be. In addition, you can also see that there is deflection on the horizontal plate that shouldn't be there. So this is an issue, and we will probably have to take care of that later on. What you can also see is, if I just take the horizontal position control here, so if I take this control and just rotate it fairly quickly, you can see this almost looks like what it's supposed to look like on a proper oscilloscope. So the only thing that's really left after we build a horizontal amplifier is to create a sync and trigger circuit, and then we could basically use this as an oscilloscope. As you can see, I built another one of these amplifier deflection boards, and I mounted both of these in here. I connected all of it up, and it seems to work reasonably well. So let's switch to the oscilloscope screen and see if we can have some fun with this. So I've got the oscilloscope switched on, I've got the camera focused at the screen, and this is just the oscilloscope running with both of the amplifier lines just open, and you can see there's some noise on there. But what I'll do now is just a couple of demos of how this works now. So I'll connect the signal generator with just a sine wave. It's a 60 Hz sine wave up to the horizontal here. And I'll just shift this around a little. So you can see this now just gives a horizontal line. But if I actually connect up the vertical channel to the same signal source, so now you can see there's just some noise on there if I touch this. And it's just me coupling in 60 Hz or 50 Hz hum. And it gives this sort of interference pattern. So if I connect this up here, you can see it gives us a diagonal line, which makes perfect sense because now basically a sine wave, but both of them are climbing at the same rate, so we get a diagonal line and it just returns to 0 again. So this alone isn't all that interesting, but the next thing is actually pretty cool. So there's websites where you can generate the corresponding waveforms to what's basically graphics like vectors. And people use this to draw pictures on their oscilloscopes, and there's some pretty cool demos out there. But what I did is I just recorded basically a picture of a triangle onto a cassette tape, and now I'm going to feed the audio into here. This should be alright. So I'll start the tape now. And at first there's nothing because there's no signal coming in. But then there's our triangle. Well, it's not a great triangle, but works. So I'll call this a success. This works fine. So the next thing I'd have to do is build a sync circuit for the horizontal. And then we almost got a working oscilloscope. So I'll leave this tape running, and there's another cool thing on there that you'll see in a second after the recording of the triangle is basically finished. Now there's some music. I actually forgot about the music I had on this tape, but yeah, this is basically a scope in XY mode visualizing music. Well, it's great.